So we're going to talk about standard scores. I want to think about what this means for the kind of data we've collected. So let's just say we're recording length, and we have some pretty established existing measures of length already. So if we use a yardstick or a ruler, whether we're measuring in meters or in yards or in feet, they're all really going to indicate the same length. So we don't really have a question as to how long something was if we're using any of these measurements. When we look at mental measurement, trying to do things in the social sciences like happiness or love, there really isn't a standard unit of measurement. And so we find ourselves comparing different measurements and not knowing if we're on the same scale. For example, if I wanted to measure how much you loved someone, one researcher might say, well, let's see how much you spent on a Valentine's Day present. And that would be one measure of love. And then another researcher might measure how much pain you would take for your loved one. And that would be a different unit of measurement. So you see how those two aren't even on the same scale. One is in dollar amounts and the other is in a pain level. And so it would be hard to compare those studies to see if they have the same results. So what would be best is if we could standardize our scores so that we could have measurements that could be comparable. So like a yardstick that could be converted to meters, doing something similar for mental measurement. So I'm going to tell you a story to help make this clear. So let's say a kid comes home from school and says, Mom, I got 98 on my math test today. Oh, and she says, that's very good, son. You must be very happy. But there's more, otherwise this wouldn't be an interesting story. Yes, but there were 200 points on the test. So normally when we say that somebody has a 98 on a math test, everybody just assumes it's 98%, 98 out of 100. But it's important that we asked how many points it was out of. And so here we can see that this kid didn't do that well at all. So the mom says, oh, I'm sorry, I guess you didn't do too well. But the kid says, well, I got the second highest score. So that's really what matters more, right? Not how many points it was out of, but really where the kid was in reference to their peers. And this is kind of what I deal with my daughter. When she comes home and tells me her scores, I say, yeah, how did everybody else do, right? So if she says, I didn't get a good score today, I go, yeah, how did everybody else do? And she says they're just about the same score as me, then I go, then you did fine. If she says I got the highest score, it doesn't really matter the number of points she got, but if she has the highest score, that's more impressive, right? So we're going to try and standardize scores, so we're not just using a percent, 98%, but instead we're going to use a reference point of where you are in reference to your peers. So just to end this story, after the kid says, I got the second highest score, mom says, oh, that's great. How many took the test? 2. Right, so that all matters. All of this context matters. So that's what we're going to do with standard scores. So we're going to use a z-score to make a standard score. And so let me just tell you some descriptors about a z-score, and then we'll see it in practice. So the z-score, it describes where a score is in reference to the group. So it tells us whether the person is above or below the average and just how much they are above or below the average. So the z-score is in units of standard deviation. So if you remember back from our previous lectures, we will describe a distribution with the mean and a standard deviation. And so what we're going to do is say, where are you in reference to the mean? Are you above the mean or below the mean? And then to tell us just how far you are above or below the mean, we'll say how many standard deviation units you are. So the z-score is in units of standard deviation. So unlike when I was saying with how much you love someone, the unit would be dollar amount. Now the z-score would be in standard deviation units. So the formal definition of a z-score, it's the number of standard deviations a score is above or below the mean. So let me show you the formula. This is what it looks like. And so these are all symbols we're familiar with, right? And so we have the z-score is equal to whatever your score is minus the mean of the population we're looking at. So that tells us how far away you are from the mean, but we want to put it in units of standard deviation, so we divide by the standard deviation. So let's say that you were above the mean. See how this x minus mu would mean you'd have a positive number? So the distance between you and the mean would be a positive number, and then we would put it in units of the standard deviation. Let's say you were below the mean. See how x minus mu would make this a negative number? So this negative number divided by the standard deviation would mean that you'd have a negative z-score. And so that would tell us you were below the mean. So positive numbers tell us you're above the mean, and the actual number tells us how far above the mean you are. And negative numbers tell us you're below the mean and how far you are. Now remember, we have to differentiate between population and sample. So this is the sample formula. And so you can see it looks very similar, but we're using the symbols for the sample. So here we have the x-score minus the sample mean, called x-bar, divided by the sample standard deviation. But the z is calculated the same way. And basically it is a reference point of how far above the mean you are or how far below the mean you are. So let's talk about an example. Let's say you're taking the SAT or some kind of test where you have to compare your numerical scores versus your verbal scores. So let's say right off the bat you find out you got a 60 on the numerical score and a 30 on the verbal. So you're not sure which one you're better at. But let's say that the mean for the numerical test was 50 and the mean for the verbal test was 20. So remember, on my story before, it wasn't just how many points you got out of how many. You had to really put yourself in reference to your peers. And this information alone isn't enough information because both of these scores are 10 points above the mean. So it looks like you did equally well on the numerical score as you did the verbal score. So you can't really tell until we've given you the standard deviation information. So if I give you the standard deviation information and then I can plot it on a picture, it now becomes clear. So here I can see on the numerical test, the standard deviation was 15. On the verbal test, the standard deviation was 5. So even though you did 10 points above the mean for the numerical test and 10 points above the mean for the verbal test, how those 10 points plot on this picture are very different. So you can see that that 30 points is far more impressive on this distribution than the 60 points is on this bigger distribution. So that's what it looks like, but let's see how the formula comes out. So remember, this is our formula. So for the numerical score, we're going to take your score of 60 minus the mean, 50, divided by the standard deviation, which was 15, and we get a z-score of 0.667. And that makes sense that it's 0.667 because one standard deviation above the mean would be 65. You see how the mean is 50, and if we go up one standard deviation from the mean, it would be 65. So it makes sense that our z-score is just shy of that 1. Now let's do the verbal. We have your score of 30 minus the 20, which is the mean, divided by the standard deviation, which is 5, and that equals a z-score of 2. Now let's see how that makes sense. So if we were just going to go one standard deviation above 20, that would be 25. We're going to go another standard deviation above that, that would be 30. So you can see we're 2 standard deviation points above the mean when we land on 30. So when we look at the calculations, it's very clear that someone did far better on the verbal score than they did on the numerical score. Now I just want to pause and say one thing that typically happens in error is sometimes students will mix up x and mu. They'll put the mu first, so they'll say mu minus x. And that would obviously give you the exact opposite orientation of where you are in reference to the mean. So the way I help students remember that is if you remember 7 years ago, I always go, your score minus the mean. It's goofy, but it'll hopefully help you remember to put your score, or whoever you're looking at. Put that score first, minus the mean. The mean goes second. So let's put this into practice to see if we can do this larger scale. Let's say that you work for human resources and you're looking at dexterity speed and I don't know what dexterity speed is. Let's say typing speed. And you've been given these scores from different employees who are applying for a position. You have to decide which one is the best candidate. Now, let's say that they use different measurements. Let's say employee A went to a testing center, and they got a score of 15, and the testing center reports that most people score around a 10 with a standard deviation of 2. Let's say employee B did some kind of online testing system, totally different system. So they got a score of 350, the mean for that online system is 300 and the standard deviation is 40. And let's say employee C had their mom report how fast they seem to type, and she reports 108, and she says out of her kids, they typically get an average of 100 with a standard deviation of 16. Now you can see those are very different scales. The employees all score above the mean on each of these numbers, but we have to decide which is the best employee to hire. So before we actually do the math, I'd like you to double check your kind of instincts and see which employee you think would be the best one to hire. So look at these numbers for a minute, maybe pause the video, and see if you can guess which employee you think would be the best one to hire, and then rationalize why. All right, let's do the math and let's see if your instinct was right. So let's do the math for employee A. I'm sorry, this is so tiny. So employee A had 15 out of 10, so sorry, 15, and the mean was 10, so it's 15 minus 10 divided by the standard deviation of 2, and their z-score was 2.5. Employee B had a score of 350 minus 300 divided by the standard deviation of 40, and their z-score was 1.25. And oops, this should say employee C. Uh-oh. I'll have to correct this. Sorry. So employee C, correct my work for me. What should it say? It should say 108 minus 100 divided by 16. So that would be 8 divided by 16. So that would be a 0.5, right? So when we do the math, we can see that we have employee A has 2.5, employee B has 1.25, and employee C, which should be written here, should be a 0.5. So based on our math, employee A should be hired. Now let's see if you had that instinct when you were looking at these numbers. What made you think that employee A would have been the right employee? Hopefully it was the thought that, wow, the standard deviation is so small that even though everybody is above the mean, employee A's performance above the mean is far more impressive because the standard deviation is so small. That means that most people were between 8 and 12. So the 15 is a far more impressive score when most people are between 8 and 12. Whereas these scores of 350 and 108 are not as impressive on their particular scales. So we're going to use an example here to talk about the properties of z-scores. Let's just say I have these fake 4 numbers in my data set, and I'm going to use them just to kind of illuminate the properties. So if I were to sum these up, that would be 10, right? And if I want to use that to find the mean, I would find that the mean is 2.5. And then I could use that to do the calculations and get the standard deviation of the population here. So let's talk about what our z-scores would look like. And this is small too, sorry about that. So if I were to calculate the z-score for the first score, it would be 1 minus the mean, which is 2.5, divided by my standard deviation, which is 1.12. And that would be a negative 135. Now let's do that for the second score. So that would be a 2 minus 2.5 divided by the 1.12, and we could see that one would have a z-score of negative 0.45. Now I can do that for 3 and 4, and I'd find that these are their z-scores. Now if we sum those up, notice that they sum to 0. That should be that way. That's because we've done our math right. And so the summing up to 0 is kind of a proof that we did them right. So 0 divided by any number is 0, right? And so that means that the mean for our z-scores will be 0. Now that works out for 2 reasons. Mathematically, it worked out because these summed up to 0 and we divided by 4. But also conceptually, we actually intended this to be the case. Because remember, the z-score is how far you are from the mean. So those people who are at the mean should have a score of 0. They are no distance from the mean. So setting each person's score who is at the mean to 0 appropriately reflects where they're at. And then if we were to do the math to figure out what the standard deviation would be for these numbers, it would be 1. And again, that works out mathematically, but also we forced it to be that way. We set the standard deviation to be 1. So if I say, how far are you from the mean, and you say I'm 1.12 points, well, that means you're 1 standard deviation above the mean, because that's what I have set my standard deviation to be, or that's what the standard deviation is. So to reiterate the properties of the z-scores then, we know that the mean of any distribution of z-scores is 0. And again, that makes sense because if the score does not deviate from the mean, it is 0 deviations from the mean. So changing your score from your raw numbers to a z-score of 0 would make sense. The standard deviation of any distribution expressed in z-scores is always 1. We made it that way. In calculating z-scores, the standard deviation of the raw score is the unit of measurement. So now let's say this was dollar amount in your pocket. These were dollar units. These are z-score units. And because these are z-score units, we're going to force the distribution of z-scores to be have a standard deviation of 1. The other thing that we need to understand is that when we're transforming raw scores into z-scores, it doesn't change the shape of the distribution, which means if we're looking at the number of scores that are 1, 2, or 3, or 4, it's not going to change when we look at how many are negative 1.35, negative 0.45, 0.45, and 135. So the proportion relation that exists among the distance between the scores remains the same. If the shape of the distribution wasn't normal to begin with, let's say this is not a normal distribution, it's not going to suddenly become normal because we translated it into z-scores. So if it started off normal, it will remain normal, but it's not going to make it magically normal if it was a skewed distribution or something.